In order to work out a good example for 2D kinematics, I wanted to work out this classic cliff problem where you throw a ball off of the edge of a cliff, and then we're going to be interested in working out all kinds of different details of the motion. I think this is a great question just to kind of work out end to end so that we can really see kind of a comprehensive example of just all kinds of different things that can come into these kind of problems. So in order to start off the problem, let's just start by organizing the knowns that we have. We know that the height of the cliff is 25 meters. The ball has been thrown 12 meters per second. The launch angle is 60 degrees. And then we also can try to break apart the velocity here into the different components. So we know that, as always in these kind of 2D problems, we're going to be interested in decomposing into x and y pieces. So vi being the total, and then we'll have a vx component of that and a vy component of that that we'll be interested in individually. So let's go ahead and use trigonometry to break this down, and then we'll get this out of the way. I'll go ahead and say vi cosine theta, which is 12 cosine 60. That's going to be equal to 6 meters per second. That'll be our initial velocity in the x direction. And then similarly for vy initial, vi sin theta, and that will come out to 10.4 meters per second. Let's also sketch out the trajectory, what it essentially looks like. As we throw the ball, we're going to get a kind of a parabola here before it descends down and lands on the ground. We're going to be interested in a variety of things. One point of interest might be the highest point in the trajectory. Oftentimes questions will ask details about that point, and then of course the final point where it finally hits the ground. That'll be another point of interest in this problem. To start off, let's analyze everything that we can about this highest point right here, right at the top. We'll try to get everything that we can, including how long it takes to get there and exactly what location is it at. In order to do this, I'll start by drawing my graphs, the graphs of the motion. We'll start with a graph of horizontal motion, Vx. The Vx motion is fairly simple for projectile motion. We know that it's going to be a constant value. So this initial velocity that we see, Vxi, which is known, it will stay at that velocity the entire time as far as the horizontal component is concerned. So why don't we go ahead and label that as this distance of the side of the rectangle, the bottom of the rectangle being the time that it takes. I'll call this delta t1 since the motion is not finished at this point. This is just the first segment of the motion, so I'll call it delta t1. The area inside this graph will be the horizontal distance traveled. Again, I'll put a 1 on that because this will be the distance traveled just during this first segment of the motion that we're trying to analyze. We'll also be interested in drawing a velocity graph for the y component. That component, we see that the ball is initially moving upward, so we're going to start at a high value on the y-axis. Gravity is going to slow it down so that vertically speaking it's declining, eventually coming to 0. And we know that at the highest point the y velocity will be 0. Not necessarily the x, but at least the y velocity will be 0, so we'll be able to draw a graph that looks like this. Again, this initial point right here is known. We call that Vyi. The amount of time is the same time we just mentioned, and then the area inside was still positioned, but this time we could call it the y position, a change in y position, and I'll put a delta y1 for that. Finally, we usually would like to draw an acceleration graph as well. There was no need to do this for the x direction since we knew the motion was totally constant. But for the y direction, let's go ahead and label one. So during this time, delta t1 that we've been looking at, the acceleration is a constant value, just the gravitational constant g, which is also known. The g will be a constant. I'll use 9.8 for that. And then during this time, this will be a delta y, a delta vy for the change in the y velocity during this time. All right, so these graphs are fairly well labeled. And now why don't we take a look at everything that we can pull out of these graphs. All the equations that we need in order to solve the problem are just going to come directly out of the graphs. So if I write out the area formulas, the area of the first graph, delta x1, will equal the sides of the rectangle, vxi times delta t1. For the next one, the area is delta y1. It's a triangle, so we'll have half base times height. That's vyi times delta t1. And then finally for this rectangle over here, delta vy will equal g times delta t1. And this is all the information that we'll need in this problem. Notice that the delta vy right here is going to be the same as vyi. This won't be true in every problem, but in this problem it will be, because we know that we start at this point up here, vyi, and we end at 0. So the change that's occurred in this time moves from this hash mark down to this hash mark, and we know that that change is actually vyi. So I'll be able to use that to do a substitution. As I consider the values of the variables that are unknown, delta x1 is unknown, delta t1, delta y1, delta t1, delta t1. These are my unknowns. This is leading me to think that the last equation is the one I should work with first because it has the fewest unknowns in it. So we can go ahead and take a look over there. Delta t1 is going to equal vyi. I'll substitute that in, divided by g. That will be the solution. When I plug in the numbers that I had previously, I get a value of 1.06, and that'll be in seconds. And now that I know delta t1, it'll be easier to go on and solve for other aspects of this motion. So if we were to take a look at delta x1, vxi and delta t1 are now known. And if we put in numbers for those, we get 6.36 meters. And then finally, delta y1. Everything in this equation is known as well. So it's already ready to plug in. And we're going to get 5.51 meters with the numerical values for that one. How do we interpret this? Let's make sure we draw this on our original trajectory. The change in the x value is essentially going to be giving us this distance right here. Horizontally speaking, the ball started at this hash mark and went to this hash mark. So delta x1 we would find on the graph there. Delta y1 we would label as this hash mark right here. We started on top of the cliff, and then delta y1 is increasing. We see that the delta y1 here is area above the axis. That's going to be a positive area, and it's going to lead to an increase in height. And as we see in the parabola, it's exactly what it does. It goes up in height, and we should label delta y1 starting at the initial height and ending at the final height. So the height off the ground, we would have to incorporate an additional h from where we started the throw. So off the ground at this point, we would actually be an additional 25 meters higher than we thought. So we might label some kind of a total height at this point as being the delta y1 plus the height of the cliff. And putting in numbers here, we would get 30.51 meters. Now that we've solved for the highest point and all the details about that, let's move on to see if we can figure out all the details of the point where the ball hits the ground. So we're now going to be interested in this point down here at the ground and trying to get all the details about that. The previous part of the problem revealed that this total height from the highest point in the trajectory down to the ground is now known. Maybe I'll call that y, where y is equal to 30.51. Knowing that, I think will make it a little bit easier to just work my way from the top of the trajectory down to the ground. So we'll start by drawing graphs to represent the motion at this stage of the problem. The first graph will be a velocity graph in the x direction. This graph is not super interesting because it looks exactly the same as it did last time. The particle's velocity throughout the entire motion in the x direction is going to be completely consistent. So this initial value here will be Vxi. The time that it takes to hit the ground, I'll call delta T2. This is the second segment of the problem, so I'm going to put a 2 on that to distinguish it from the first. This is an unknown at this point. I don't know how long it takes, but hopefully we'll be able to figure that out in the course of the problem. And then the area inside here will represent delta x2. It's the amount of horizontal distance traveled during this time of the problem. We'll also be interested in a y velocity graph here. If we start at the highest point in the motion, we know that the highest point, Vy, is going to equal 0. So I'm going to be starting at the origin right here. And as gravity pulls the particle downward, then the velocity will be increasing but in a negative direction. It'll be going faster and faster, but it's going to be going downward the whole time. So I really need to extend my velocity graph downward, and we'll get a triangle like this. This value over here on the axis would be the final velocity in the y direction for the particle. This is also unknown at this point. I don't know how fast it hits the ground, but at least let's get this labeled so we can see what all the different parts of the graph, what they represent and how they fit in. Same time, delta T2, and then the amount of position that has been covered, I'll call delta Y2. And delta Y2 is this full distance over here. That full distance from the top, the highest point in the trajectory, down to the ground, that is that distance that's been covered in this segment of the problem. So delta Y2 would be an appropriate name for it. And then as before, we can do a quick acceleration graph in the y direction. Again, this is not terribly interesting. As before, it's just g. The value of the acceleration on the axis would be g, and the amount of time that's elapsed, delta T2. The area inside the triangle, we could call that a delta Vy, and then maybe I'll put a 2 on this to distinguish it. It's not the same delta Vy as we had on the last part of the problem. So these are a set of graphs for what's going on in this segment of the problem. Everything that we need is going to come from the graphs and equations that we can draw just based on simple geometry. So again, why don't we sketch out what the area of each of these graphs is going to represent. First graph gives us this. Second graph is a triangle. And the third graph So all the results here are very similar to what it was on the previous part of the problem. The main difference is that different things are known, different things are unknown. I do not know how far the ball travels, nor do I know how long it takes. But this time the y height is known. That 30.51, that is the total amount of distance it's going to fall to get from the highest point to the ground. So that's going to be a known, whereas the velocity at the end and the time would be unknown. Notice over on this part, the last equation, that the delta Vy here, this is going to be the same as velocity final in the y direction. How do I know that? Well, we started at this point 0, and we ended at this point down here. So the amount of change going from this hash mark to this hash mark is indeed VYF. And if I realize those are the same variable, then I'll be able to take advantage. Now it is an unknown at this point, but I will be able to plug it in over here to combine these equations together. Finally, delta T2 is also unknown, as we've said. So there are no equations that have a single unknown, but that's fine. We just realized that the delta Vy2 is the same as Vfy, and so I'll be able to substitute this into this equation over here, which will eliminate one of my unknowns and give me an equation that I can solve. So what will that look like? Delta Vy2 will equal 1/2 G delta T2 will be plugged in. Then we have another delta T2 that was already there. So we're going to end up with a total of delta T2 squared. And then I just need to solve for delta T2 squared. Delta T2 squared, if I multiply 2, I'll have 2 delta Y2. I'll divide by G to get delta T2 squared by itself. And then why don't we go ahead and just square both sides. The square there will go away, and we'll get a square root on this side right here. So this successfully solves for delta T2 only in terms of things that are already known. If I plug in the numbers for this part, I get a time of 2.50 seconds. So this will be the amount of time that it takes in total to get down to the ground. With delta T2 now known, we can go back over here, solve for delta x2. Vxi and delta T2 are both known. If I plug in numbers for that, I get a distance of 15.0 meters. It might be interesting, of course, to try to find like a total distance, a total delta x, which would simply be the combination of the delta x1 and delta x2. We had solved for delta x1, which was the amount of distance covered horizontally in the first segment. Delta x2 would appear right here, the amount of distance covered horizontally in the second segment. And we can put those together to get a total. Putting in the numbers for that, we get 21.3 meters. So that would be an interesting result we could give for this problem. If we happen to be interested in what the final velocity actually was, we could come back over here to these equations. Delta Vy2 we said was the same as Vfy. And then G and delta T2 are now known. If we plug in those numbers, then we get 24.5 meters per second as a final velocity for this. And then finally, if we happen to be interested in the total time for the entire motion to occur, that would just be the time that was elapsed during the first segment added to the time that was elapsed for the second segment. That looks like, just looking at the numbers that we obtained, is probably going to be 3.56. So I've tried to, in this example, to just go through almost every single variable you might be interested in solving for. A cliff problem like this could ask for a variety of different things, and whatever has been asked for, we were able to step through the problem just step by step using our graphs in X and Y to pull out the information we needed and eventually solve for all the details of everything that was happening all the way through. It might be helpful to comment on some of the strategy that we use to try to take this problem apart. It's a fairly long problem if you really want to solve for every little detail of it, and there's a lot of things to keep track of. I guess first and foremost, it would just be helpful to make sure to try to organize everything that you do. Don't try to solve the entire problem at once. Just isolate pieces and take it step by step as you move through. Every time you figure something out, add that to your list of knowns and just try to stay organized and just kind of move your way kind of step by step through the problem. You'll notice that the whole key to this problem, kind of taking it apart, was to try to cut the problem apart at this highest point up here at the top. We were able to essentially segment this problem into two subproblems that we only solved one at a time. When we concentrated on the first part, things did not become too overwhelming, the graphs did not look too overwhelmingly complicated, and we were able to step through that and try to figure it out. Then when we did the second part, we had a lot of knowns, and so we were able to concentrate only on the new information that was going on in the second part. So anytime you see a projectile motion problem like this, the recommendation is to take the problem apart into the two pieces, and it'll make getting through the entire problem a little bit simpler. There are methods available that enable you to deal with a projectile motion problem all in one shot. It doesn't require you to take the problem apart, but of course those are going to involve the quadratic equation, so although you save a little bit of work maybe by dealing with a single problem instead of two subproblems, you also kind of end up doing a little bit more work in terms of the quadratic equation, which we were able to avoid by just splitting the problem into pieces. So I find that splitting the problem apart tends to be the most straightforward way to approach it, and the easiest way to organize all the information. So that's the recommendation for a kind of a large and long problem like this. Even if you're not asked for details about the highest point, I would still recommend taking the problem apart into the two parts. Other problems, of course, essentially only ask for information about the highest point. If that's the case, then basically you just solve up to that point and you never have to write down anything that happens after that. So those problems would be quite a bit shorter and quite a bit just less in terms of what's being asked for. Other kinds of problems also provide simplifications. So the cliff problem does tend to be one of the most complicated problems that we have in 2D kinematics. There are many 2D kinematics problems that rather than being up on a cliff, it just asks you to execute some motion like throwing a ball. And in a problem like this, what we want to notice is that, again, we'll take it apart with the highest point and try to basically divide the problem in half. But the really nice thing about these kinds of problems is that you have an exact kind of a symmetry. If you look at the parabola there, we can tell that the parabola is exactly symmetrical on the left and the right. So when we go through our first segment of the problem and solve for everything just kind of leading up to the highest point, everything else that happens in the problem basically is already known because we know that it's going to come back down exactly the same as it went up. The velocity when it gets to the ground will be the same as it started. The amount of distance covered will be the same in the x and y directions. Basically everything is symmetrical. It's just one you're going up, and in the second half the ball's going down. So these kinds of things can really make the problems a lot easier to solve. Another way to represent what we just said would be to sketch out a VY graph. So these graphs starting up here at a high velocity would decrease and then keep going down and end with some final velocity down here. But again, the key is to notice that there's a symmetry. These two triangles, the triangle above the axis and the triangle below the axis, are going to be exactly symmetrical. And so there's no real need to solve for the second half of the problem. Once we've solved for everything leading up to the highest point, then we'll already know all the answers for what happens after that. So I think this highest point strategy of taking the problem apart into two subparts is especially beneficial when you have a symmetry and you're able to basically only solve one half the problem, and you basically get, you know, two for one. Noticing that symmetry would be a really important thing to be able to do to simplify these kinds of problems. So symmetrical problems would be seen to be a lot nicer to go through. Other kinds of problems would only ask you to you know, start with a horizontal launch. So maybe you have a cliff or something like that, but the ball is launched directly horizontally. These kind of problems, or these variations on the cliff problem, are also quite a bit nicer to solve because, again, you don't have two halves of the problem. Your velocity graph for a problem like this would actually be starting at 0 for the y velocity because you're coming off the cliff in a completely horizontal direction. No y velocity at all. So you start at a y of 0, and then you're decreasing that as gravity pulls it down. So what essentially we see here is the only thing in this problem are graphs that look like what we drew in the second half of our problem in this example. So again, there's not really two halves of the problem that are needed if you have a horizontal launch. And these horizontal launches are another thing that you can look out for that would actually fairly simplify the work that was shown in this example. Basically only concentrate on the second half of the example to understand how to do any kind of a horizontal launch problem. Finally, we also might have a kind of a problem we can imagine where we basically just throw the ball straight up. If we imagine that just we're on the ground, we might say we throw the ball straight up, and then we come right back down on top of and hit the ground. So we'll have a highest point and we'll have a ground level. So for this kind of a problem here, the Vy is going to look exactly the same as it did for the ball thrown forward. Since we're only concentrating on the Vy direction, vertically speaking, both this problem with the ball traveling forward as well as the one with the ball going straight up, those are going to be exactly the same vertically. So they have the same y velocity graph. They're also symmetrical if you are throwing it straight up and it coming back down to the same position. You'd be able to rely on a symmetry. And then furthermore, those are nice because nothing is happening with the x velocity in that problem. So it just kind of simplifies the amount of stuff that's happening. So hopefully this slide here gives you a good summary of some different variations you would see in a projectile motion problem with two dimensions. Really, most of the variations you would see would be simplifications of the example shown in this video in some form or another. And if you can handle a cliff problem like shown in this video, then you should feel really confident in solving almost any projectile motion problem.